exponential functions, and this is carrying on from exponential equations and expressions from last one. So here we go, exponential functions. Now, a nice place to start is looking at our most common functions. It just gives us a nice idea of the flavors that we can get. So let's go x, and let's go f of x is going to be 2 to the x, and then we've got g of x, which is going to be 3 to the x, and then we've got h of x, which is going to be half to the x. Okay, and then we're just going to draw some grids across here. Now, you've already done this exercise in class, but it's nice to have a bit of a play around with the algebra before we look at the graph from Desmos on the right. So let's chuck in some values. Let's go -3, -2, -1, 0, 1, 2, and 3. And let's fill this in. So the first one's 2 to the -3, 3 to the -3, and a half to the -3. And let's just do 2's first. So 2 to the -3 is going to be 1 on 2 cubed, which is the same as 1/8. 1/8, I should say. Then we've got 1 to the 4. We've got 2 to the -1 is a half, or 0.5. Then we've got 1. Anything to the power of 0 is 1, 2, 4, and 8. Next is going to be 3. There's going to be 1 on 27, 1 on 9, 1 on 3, 1, 3, 9, 27. The next one we have is a half. So the reason I've written this out is that 2 to the -1 on 3, we know is going to become 2 to the 3. So this is going to become 8. Next one, 4, 2, 1. Then this goes to a half. Half to the 1 is half. A quarter and an eighth. So we can see a nice little relationship between these two. The 2 to the x and the half to the x is that it seems to be mirrored, right? So a reflection in the y-axis of both of these. Now, with this in mind, we can see that what happens if x is getting really, really big for these functions? Well, 2 to the x and 3 to the x, we can see it's gone 1, 2, 4, 8, so 16, 32, 64, 102, It's going to get larger and larger, quicker and quicker. Same for 3 to the x, but even more so. So as x gets larger and larger, we can see that this function is getting larger and larger, and even more so than 2 to the x, so it's going to be steeper. Half to the x is a different story. As x is getting larger, we can see that's going half, the 4th, 8th, 16th. So this value here is constantly being halved. Now we know if we keep halving something, it's just going to go essentially to 0, but we'll never get there. Okay, so we're hitting something called an asymptote for half. Now let's go the other way. As x is going to negative infinity, so when x is getting a larger and larger negative value, it's going half, quarter, 8th, 3rd, 9th, 27th. So that means this seems to be tending towards 0 both these ways, and this one is getting bigger and bigger. 1, 2, 4, 8, so 16, 32. So we can see that this function is going to get bigger and bigger and bigger. So this is called our behavior. Let's chuck these in and see if we're right. And I'm just going to use y in this case. 2 to the x, y is equal to 3 to the x. And then we've got y is equal to half to the x. Okay. Now we can see that here's in blue is 2 to the x, and I think I can get rid of these, yeah. In blue, this is 2 to the x here, so it's quite steep. 3 to the x, even steeper. And then half to the x, we can see is going the other way. So we can talk about these functions here, and I'm going to take a screenshot of this, okay, like that, and just whack it in. Hopefully this works. Oh, look at that. How good's technology? And let's start drawing on here. So this one here is, let's go blue. Y is equal to 2 to the x. In green, y is equal to 3 to the x. And then in purple, which I haven't arranged, there's a purple, y is equal to half to the x. Okay, now we need to be able to describe these functions and also plot them and then also transform them. So these are our base functions, and we need to know the key features here. Once you know that, we can start transforming them and that kind of stuff. So let's talk about our key functions. Now I'm going to move this across and talk about them. So, key features. We can just write these out. Y is equal to 2 to the x, y is equal to 3 to the x, and y is equal to half to the x. And then we can talk about maybe points, asymptotes, behaviors, and domain and range. Okay, I'm going to make a table out of this. Here we go. So let's go y is equal to 2 to the x. Key point, definitely 0, 1. Right, we can see, in fact, they all go through 0, 1. So 0, 1 is 2 to the power of 0, so that's pretty handy. Another point we can say is that 1, 2, and maybe another point you could say is if I'm going -1, it's going to be a half. Asymptotes, we can see that y is equal to 0 is an asymptote. Behaviors, well, remember behaviors, it goes x approaches infinity, and as x approaches negative infinity in this case, y is doing what? So what's the y value is doing? X is going to positive infinity. We can see that this function is going to positive infinity as well. And as x is going to negative infinity, we can see that y is going to 0, and it's approaching from the positive side, so you write 0 plus. And that ties in with our asymptote there, y is equal to 0, never reaches 0. Domain and range, well, we can say that the domain is going to be, well, x can be over here, 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 here. Are there any values of x that are going to break our function y is equal to the x? No, the x do continue there, it just goes off the grid. So we can say x is all reals, okay? That's our domain. The range, the y values, we can say, yep, we've got y values all above 0, but there's no y values at all down here. Therefore, this graph only exists for y greater than 0. Why do we say equal to? Because there's an asymptote here. It never actually reaches 0. That's the concept of the asymptote. Let's move on to the next one. Now, these are incredibly similar because both of these functions are in growth. Okay, we can see here these are both in growth, and this one is in decay. Right? So we can basically copy a lot of these concepts across. So here we go. This is y to the 3x, and I'm just going to change this one to green to match up with the color we've used. Key point 0, 1, 1, 3, and -1, a third. Asymptotes, y is equal to 0. These are identical, and these are identical. So when a graph is under growth, these are both under growth, we can see that these asymptotes, behaviors, and domain and range stay exactly the same. Let's look at our final function that we've sketched before, which is in purple. So I'll switch to purple. This one here, still 0, 1, but then it's flipped. So we've got 1 is going to be a half, and -1 is going to be 2. So we can see that this is 1, 2, this is -1, 2, this is -1 half, now it's 1 half. So we can see it's reflecting over this y-axis. Asymptotes, y is equal to 0. Behavior, this is different. So as x is approaching positive infinity, we can see that y is actually approaching 0 plus, and as x is approaching negative infinity, y is approaching infinity. Right? And domain and range, exactly the same. So this is the exponential function. Now we can use these base features to maybe describe some new things. So I'm just going to make up some questions here. So I'll press enter here. Okay, so go here. And maybe we might be asked, can you go, let's consider a graph, let's call it k of x, and it's equal to 2 to the x plus 2 plus 3. And let's go another one. M of x is equal to negative half times 3 to the x take 4. Okay. Now, some classic questions might be what's the domain and range of these functions? So what we need to do in this case is consider what's going to happen with our transformation for each of these things. So let's consider our domain and range. Now, if I move this graph to the power of x, if I move it left 2, then up 3, the domain is going to stay the same. It can be still any value. Nothing is going to break it. So the domain is going to stay the same. But what about the range? Well, we know that in exponential functions, the range is impacted by the asymptote. So therefore, we've got to look for that asymptote. So where is the asymptote? Now, we know that if we're shifting an asymptote along, so picture this graph here, 2 to the x, if I move this to the left, that hasn't changed my asymptote at all. Still y is equal to 0, isn't it? So we know that any horizontal translation isn't going to affect it. However, there is a plus 3. So therefore, the whole graph is going to move up 3, and this includes the asymptote. So we know that the asymptote is going up 3. So therefore, we can now answer this question that y must be greater than 3 now, right? Because the graph has gone up 3. Therefore, the asymptote y is equal to 3. Okay, and you may be asked to sketch this function, for instance, but yeah, I mean, this is a classic thing here. Can you describe the behavior? Yeah, this one's not too bad either. It's just the same because it's just holding shape. Now this one over here, we might be asked to do the same question. Now, this one here I like because we need to consider what's happening to the function. Now, you're using the CBAD, and we're going to consider what's going to happen to our asymptote here. So the asymptote is at y is equal to 0. Now let's consider our transformations here. We've got this negative half, and we've got this negative 4. Now this part here represents our a, and this is our d. And what's that going to do? We can see it's going to be times by a half along the y, so it's going to be a vertical stretch by a factor of a half along the y, and it's going to be reflected in the x, and it's going down 4. Now, if I think about this, if I reflect asymptote over y is equal to 0 along the x-axis, it's going to stay there. So the y is going to stay the same. So this is the reflection. So no change. Then what happens if I stretch all my y values by a half? Well, if I timed all my y values by a half, y is still 0, right? So the only thing that's going to impact this asymptote is going to be this take 4, right? I'm shifting the graph down 4, including the asymptote. So here's my new asymptote, y is equal to negative 4. So now we can answer this question. We can say that the domain x still all reals, but y, the values has to be greater than negative 4. Or is it? Well, I really like doing a little sketch of this function, okay? A real common mistake is to keep it like this. But we know there's also been a reflection. So what I like to do is consider, I've got 3 to the x here, which looks like this. Then consider what's happening. Well, you've got your key point 0, 1. Where's 0, 1 going to go? It's going to get reflected, then it's going to get halved. So it's going to go to 0 half, right? Then it goes down 4, so it's negative 4.5. Now, if you picture this, we've got a asymptote at negative 4, and then the graph has been squished. So it's going to look like this. So therefore, the range isn't y is greater than negative 4, it's going to be less than negative 4. Because of that reflection in the x-axis. Okay. Great. So this is a bit of an overview of exponential functions and also these values here. The last special case is e to the x, and it's a very straightforward function. It's just an irrational number. And e to the x slots itself in the middle here, okay? So I'll go on here and plot it. You should see this is the natural exponential, which is simply known as e, and we see it's 2.71828, and it's just really annoying to write that out all the time. That's why we use that function. And we can see that it slots in between 2 and 3 because it is specifically 2.718. Okay, and more or less we do exactly the same principles with this. The y asymptote still identical to the other functions. It's just a growth function. So an e function holds all the same attributes as these functions here, except that your key points is 1 e to the 1. Okay, so this is our review here. What we're going to do is look at some applied situations. And this is sort of using your ClassPad. Unfortunately, my ClassPad app's not working at the moment, but you might find this useful. I'm going to jump on the OneNote here and just go under where is it? Exponents. I'm just going to grab a question from here. So you might find this one here. We did this one in class already, but I thought it might be good just to revise what you could get. Okay, here we go. And we make it bigger. Now, usually this is a calc question as well, so I'm going to use my Desmos over here to help me graph this, and I'll read out the situation as well. A scientist monitoring a grasshopper plague notices the area affected by the grasshoppers is given by this function here. So I'm going to write this out as y is equal to 1,000 times by 1.15 to the power of n. Okay. Oh, let's go x, sorry. And we may note that here on a graph it's not going to work. So on your ClassPad as well, you've got to consider where is this graph going to be. Well, I know this is going to be my starting value. So this value at the front for a function of this sort is going to start at 0, which is my initial population for that. I'm going to change my y-axis. I might make it 5,000. And I might go from, actually, that's not too bad. And since it's an applied situation, in weeks after, I don't really care about negative values. I might go negative 0.1 as to the axis, and then put maybe 10. That seems okay. And this is all about adjusting. So, we can see that this function here is showing okay, and it's nowhere near the exponential we're used to, just because it's basically how you're viewing the graph. Okay, now that we have a function, we can answer our questions. Now, first step, let's write this out in terms of a general form, our equation. So a n is equal to a0 times by r. There's so many letters you can use here, b to the n or whatever. Now, a0, when it's in this form, is our original population. Okay. So that's the first question. Can you find the original affected area? Now, if you don't believe me, you can sub in 0. And we know that anything to the power of 0, i.e. this 1.15 to the 0 is just going to become 1. So therefore, there we go. Now, since this is an applied situation, we need to say 1,000 hectares, the original affected area. So just use the units. For B, find the affected area after 5 weeks and 10 weeks. Now, I'd recommend using your ClassPad for this, and you can do an X calc and a Y calc to find these values. So we need to find 5. So I'm going to go across to 5 and hopefully jag it. There we go. So we can say that after 5 weeks, and I can write it like this, A5 is equal to, and we're going to go 3 sig figs here, 2010. And that's hectares, so we can just write H. And A10, let's go across here. Oh, is it going to fit in? Come on. Oh, lucky, just in there. 4050 hectares as well. Next, it says draw the graph of the affected area over time. Now, since we have 3 points, we should be able to draw this okay. And to be honest, normally they give you graph paper and stuff. We're going to give it a crack here. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Good. And let's go. That's 1,000. That's a break. 2,000, 4,000, 2,000, 3,000, 4,000. 2, 4, 6, 8, 10. And then we're going to sketch in these points. So we've got 3 points here, which should be enough for this. So let's put in 1,000. Let's go to green. 0 is 1,000. Nice big dots to represent this. 2 is 2010. 2010. So I'll put it about there. And then we've got, oh, what am I doing there? Sorry, that's meant to be 5, right? 5 is 2010. And then I've got 10 is 4,050. And we can see that this is going to be slightly exponential. And with this strategy here, I'd recommend just doing lots of little lines. And you want to sort of have a little bend in your lines. Oh, so this is not very good. So I'll start once more. But there's a bit of an art to it. You want to start leaning towards the outside, but slowly making your way in to the function. They're not so straightforward like that. There we go. And since this function continues, I'm going to draw an arrow here, right? But I'm not going to draw an arrow over here because it doesn't make any sense having a negative value. Now this is area in hectares, and we've got weeks here. Here, n is the weeks. That's a variable on the x-axis. So instead of x, they're using n, and over here they're using a. Okay, so we've sketched that out, and yeah, that's it. Use your graph or technology to find how long it would take for the effective area to reach 8,000 hectares. As you can see, I'm in a bit of a crisis here because they've said 8,000 and I've gone to 4. So I'm just going to zoom out here and I'm going to change my axis to 10. Okay, and you can see I don't have enough x values, so I'm going to change this to 20. There we go. Now, a really handy thing to do here is to draw a line. If you're trying to find this, so area is going to be when is it 8,000? I really recommend this because then you can just find your intersection using your class pad. So here we go. We've got our intersection, and I'll just take a screenshot of that just to make it pretty. Paste it in. Okay, and let's talk about that. Here's our intersection. I'll highlight that. And then we want to make a sort of a sensible answer here. D. After, and let's go 14.9 weeks, so 3 sig figs. The area affected is 8,000 hectares. All right. After 14.9 weeks, the area affected is 8,000 hectares. Okay, so there we go. We've looked at functions in this lesson here, how to sketch the exponential function, how to transform, find the domain, behavior, and then some applied situations. This one is a growth situation. You can check your books, but there is also decay questions as well. Okay, hopefully this video is useful. In the next few videos, I'll be looking at doing a recap of the logarithms. Thank you.